This video will cover the second derivatives test. This is part 2 to section 2.7 on optimization. Let's talk about the second derivative and how we can find extreme values of f. The concavity of a function can also help us determine whether a critical point is a maximum or a minimum or neither. In section 2.6, we define concave up and concave down, so you may want to review that video. For example, if a point is at the bottom of a concave up function, then the point is a minimum. To use the second derivatives test, we start by finding all critical points of f. That's where the first derivative is either set equal to 0 or undefined. Then we find the second derivative and evaluate at those critical points. If the second derivative evaluated at a critical number is negative, then f is concave down and has a local maximum at x equals c. If the second derivative at the critical number is positive, then f is concave up and has a local minimum. If the second derivative is 0, then f may have a local minimum, local maximum, or neither. A function in values of x so that f prime of x equals 0 are given. We use the second derivative test to determine whether each point is a local maximum or a local minimum or neither. So we actually don't need to find the critical numbers because they're given to us. So what we'll do instead is find the first and second derivative. That way we can use the second derivative test. So the first derivative is 4x cubed minus 16x, and then the derivative of negative 2 is 0. The second derivative is 12x squared minus 16. Then we'll use the second derivative test to identify if negative 2, 0, and 2 are a maximum, minimum, or neither. We'll do that by evaluating the second derivative at each of those numbers. So plugging in negative 2, the second derivative evaluated at negative 2 is positive 32. So when the second derivative is positive, the function is concave up, and then there's a minimum at that value. We'll need to go back and plug in negative 2 into the function to find the point at which the local minimum occurs. Let's evaluate the second derivative at 0. The second derivative is negative 16. When the second derivative at a critical number is negative, that means that the function is concave down around that interval, and we have a local maximum. Finally, let's evaluate the second derivative at positive 2. The second derivative is positive, and so we have a local minimum. Now we'll plug in negative 2, 0, and 2 into the original function to find the associated points. So in conclusion, there is a local minimum at the point negative 2, negative 18, and the point 2, negative 18. There's also a local max at the point 0, negative 2. To find global extrema or global maximum and minimum, the only place where a function can have a global extreme are critical points or endpoints. If the function has only one critical point and it's a local extreme, then it's also a global extreme. If there are endpoints, find the global extremes by comparing y values at the critical points and at the endpoints. When in doubt, graph the function to be sure. We want to find all critical points and global extremes of f of x equals x cubed minus 3x plus 5 on the interval from negative 2 to 1. We'll start by finding our critical numbers. I'm going to use the second derivatives test in this video, but you may use the first derivatives test. We'll compare all of our critical number values to our endpoint values and then make our final conclusion. Let's start with the first derivative, set equal to 0, to find our critical numbers. The first derivative is 3x squared minus 3. We'll set this equal to 0 to solve. We see that we have critical numbers of x equals negative 1 and x equals 1. I'm going to take a moment to plug those into the original function to find the points at which our critical points occur. These are just candidates for local extrema and global extrema. We won't know until we continue with the second derivatives test. Now that I have my critical points, let's take the second derivative and plug in the critical numbers to determine if there may be a local maximum or minimum at those points. The second derivative is 6x. We'll evaluate the second derivative at negative 1. Since the second derivative is negative at negative 1, our original function f is concave down, and so we have a local maximum. Let's evaluate the second derivative at positive 1. Since the second derivative evaluated at positive 1 is positive, the original function is concave up, and so there will be a local minimum. Now, to determine if this or the endpoints of our given interval are local or global extrema, we'll compare by evaluating the endpoints of the function as well. What we can see is that we have at our endpoint 1, a local minimum occurred, and so it's an endpoint and a local minimum, so it's a global minimum. And then at f of -2, it's also at the same value, so there's a global minimum at -2, 3 as well. So we'll say global minimum at -2, 3 and 1, 3. And there's a global maximum at our local max because there's no other higher value over our closed interval. We can take a moment to look at our graph on Desmos over the given interval. Okay, when we look at our function in Desmos, notice that the window is from -2 to 1. That's in the x direction. We have our -2 point here. Get close. -2, 3. We have a maximum, which is at -1, 7. Notice that over this specific interval, it is our global maximum because it's the highest point over the closed interval. And then we have our other global minimum at the point 1, 3, which happens to also be our local minimum as well. In the next video, we'll combine all of these ideas to curve sketch using the first derivative and the second derivative and other known information about the original function.